Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 4, Contextual Applications of Differentiation, and we are on the last new topic of Chapter 4, Topic 4.7, which is what's called L'Hopital's rule for determining limits of indeterminate forms. Enjoy today's notes. All right, 4.7. We are on the final lesson of Chapter 4, and we're talking today about this thing that is called L'Hopital's rule. First off, before we get into it, a couple things. Sometimes you will see this name L'Hopital spelt with or without an S. So sometimes you might see it like this. Generally, that's like a regional thing. I want to say in different countries maybe they come up, but they come sort of in two different ways. They're both the same name. Generally, if I'm pronouncing this and trying to read this out loud, I just make the H silent. So if I'm trying to read it, I say L'Hopital. L'Hopital is the way that I would pronounce this. Now, 4.7 is actually about limits. It's been a few chapters since we've talked about limits. In fact, limits were all of Chapter 1, which we did. But there's this one sort of straggler topic which we throw into Chapter 4 because it's a special rule for limits that deals with derivatives. And way back when in Chapter 1 at the beginning of this year, we didn't know how to take derivatives, so it wasn't appropriate yet to talk about this cool rule, L'Hopital's rule. So, in general, let's do a little bit of review from Chapter 1 on how we do these limits. Recall, when evaluating limits, first try this thing that's called direct substitution. So limit as x approaches 3 of 2x minus 5 over x. Generally, the first thing you do when you see a limit problem is you try plugging in whatever x value they gave you, and you hope that you get an actual answer, because then you don't have to do anything else. If you get like indeterminate form, we've got some tools in order to help solve these problems, and we talked a lot about those in Chapter 1. We'll talk about a new tool that we've got today called L'Hopital's rule. So what would that look like in this problem? Well, that would be equal to 2 times 3 minus 5 divided by 3. 2 times 3 is 6, 6 minus 5 is 1, and then that's being divided by 3. So this limit would be equal to 1/3. That is a nice problem that we can set up and we can solve using just direct substitution. Nothing special for this particular problem. However, if we look at this problem here for number 1, right here, the limit as x approaches 2 of x squared minus 7x plus 10 divided by x minus 2. Again, our go-to method here is when I try direct substitution. If we do that, we see here that this is 2 squared minus 7 times 2 plus 10, all divided by 2 minus 2. In that numerator, we've got 4 minus 14 plus 10 divided by 0. And so this looks like this is 0 over 0. Now, for those of you playing at home, sort of two things that I would sort of remember. The first is that this thing called 0, this 0 over 0 is a special form, which we refer to as indeterminate form. Indeterminate form. And in general, indeterminate form is when you do direct substitution and you get 0 over 0 or infinity over infinity. Could get either one of those two things if you're looking at indeterminate form. So, with that said, the other thing that I would also want to mention is we're going to be focused really today on showing proper notation. Notice that we did our direct substitution here in the step. We got these 2's, we plugged them in, we got 0 over 0. Now we know that this limit cannot equal 0 over 0. It can't equal something that's being divided by 0. So I would just go back after I do this and make sure that I'm saying that this is not equal and being very clear in that work. This is something frequently on the AP exam where during the free response section, students are showing their work, they try to use L'Hopital's rule, and they say that the original limit equals 0 over 0. That is something that is that you can lose points from doing. So you want to make it clear that whatever work you're doing to show that it's in indeterminate form is like side work, and you're not saying that it's actually equal to here. Now, we can go a couple of different ways to solve this problem. We know that one of the ways that we talked about fixing and dealing with indeterminate form is like trying to find factors. So an old way, let's go with the old way first, back from chapter 1, is we could try factoring that numerator and the denominator and see if anything cancels. If you factor the numerator, right, we could see that that's going to be what? X minus 5 times x minus 2 divided by that x minus 2. And we see those x minus 2's cancel. So this is equal to the limit as x approaches 2 of just x minus 5, which we can then substitute in and see that this limit is going to be 2 minus 5, which is negative 3. So that is the old way that we would do this problem. And this is a fine way to do it, right? Like there's no problem with like actually using factoring, but sometimes when we get these indeterminate form problems, it's not possible to factor, at least not, easily. So we have this new rule, which is called L'Hopital's rule. And let me show you how that works. So the first piece that we would need to do in order to use L'Hopital's rule is to show that the original function would give us indeterminate form. Remember, again, we do not say that they are equal. They are not equal to 0 over 0, but I'm going to state that it's indeterminate form here. And that's going to allow me to use this thing called L'Hopital's rule, which I guess I'll use a different color for this piece. And what we're going to do here is we're going to actually say, okay, the limit as x approaches 2 of this x squared minus 7x plus 10 divided by x minus 2, this is first off a candidate to use L'Hopital's rule because the direct substitution gives us indeterminate form. But what the cool thing is we actually can take the derivative of the numerator and the derivative of the denominator and try direct substitution again. So L'Hopital's rule actually shows that this limit is actually equal to the limit as x approaches 2. Notice that the x approaching the 2 did not change. That stays the same. But we're going to take the derivative of the numerator, the derivative of the denominator. What's that going to be? So we have 2x minus 7 would be the derivative of the numerator. And in the denominator, that derivative is 1. Now, once we've done this L'Hopital's rule, right, which allowed us to simplify this limit, we can try direct substitution in again. We're going to plug 2 in for that x and see what we get. That looks like this is going to be 2 times 2 minus 7, which is 4 minus 7, or negative 3, just like we said over here using our old way. This is nice, certainly in problems where you just can't factor, where there's no easy factors to deal with, but notice that it gets you the same answer with this different way. So let's step back and talk about what L'Hopital's rule is and how we know we can use it. The statement of L'Hopital's rule says, suppose f of a is equal to 0 and g of a is equal to 0. So in this case, if I take the limit as x approaches a and I plug in a into the f function and into the g function, that I get 0 over 0 or infinity over infinity, aka indeterminate form. So if we have something that gives us indeterminate form, L'Hopital's rule allows you to apply the following. Simply, if your original function was the limit as x approaches a of f of x divided by g of x, that's going to be equal to the limit as x approaches a of f prime of x divided by g prime of x. Again, the reason why we're learning this rule now is back in chapter 1, we didn't know how to do derivatives, but we have this really cool thing that we can do now that we know how to do derivatives, which will make some limit problems a little bit easier for us, which is really nice. Also, a cool thing about L'Hopital's rule, which I'll mention now, is sometimes when you do these problems, you take the derivative of the numerator, the derivative of the denominator, and you do direct substitution again, and you get indeterminate form again. In cases like this, there's some problems where you just can do L'Hopital's rule a couple of times, and then we'll get you to an answer. I think we'll see one of those later. I think probably looks like problem number 5. We'll see that, and maybe problem number 4 as well. But that's just sort of a heads up. You can use L'Hopital's rule multiple times in a problem as long as you're getting indeterminate form each time you do that direct substitution. Nice. Let's see this for number 2. Actually, even before that, I want to mention, hey, be careful. Notice here that this rule is not the same thing as quotient rule. This is not the quotient rule. for derivatives. Remember, we learned the quotient rule back in chapter 2. The quotient rule is the rule that we use for two functions that are being divided and we're taking the derivative. Notice that this is not the same thing as that, right? We're not doing low d high minus high d low all over low squared. That is a lot, that's something totally different from this L'Hopital's rule, where I just get to take the derivative of the numerator and divide it by the derivative of the denominator. Two different things. All right, number 2, evaluate each limit and use L'Hopital's rule when possible. First things first, I'm going to try that direct substitution. Let's see what happens. We get 2 minus 2 divided by 3 times 2 cubed minus 6 times 2 squared plus 2 minus 2. If we do that, that looks like that's 0 over what? 8, 24 minus 24 plus 2 minus 2. That's 0 over 0. And so I'm going to state here, hey, we got indeterminate form. Now, by me stating this, I'm going to do this as side work over here. Notice that I'm not saying that these are equal, right? This does not equal 0 over 0. We would not want to do that. That would lose us points on the free response part of the AP exam. But by showing that this is indeterminate form, this is now going to unlock our ability here to take the derivative of the numerator and the denominator and apply L'Hopital's rule. If we want to be really clear about the best case for what the AP exam would be looking for here, we would really want to show our work and say that the limit as x approaches 2 of just the numerator, x minus 2, that's equal to 0, and that the limit as x approaches 2 of the denominator, 3x cubed minus 6x squared plus x minus 2 equals 0. And I'm going to say, so L'Hopital's rule applies. This is really like best case scenario how you would show your work on the AP exam, showing that the numerator, if you do direct substitution, gives you 0, and the denominator, if I take the limit, gives us 0. Therefore, L'Hopital's rule applies. Then I can just go on and actually use L'Hopital's rule and find out what that limit is. So this limit as x approaches 2 of the x minus 2 over 3x cubed minus 6x squared plus x minus 2. If we take that derivative, that's going to be equal to the limit as x approaches 2 of 1 in that numerator, divided by what looks like 9x squared minus 12x plus 1. And I'm going to try to plug in 2 again and see what happens. This looks like this is going to equal 1 over 9 times 2 squared minus 12 times 2 plus 1. So that is, 36 minus 24 plus 1. That should give us 13 in that denominator. And that is going to be our answer and our limit for this particular problem. Recap, just really quick. I did direct substitution originally just to see if it were to give me indeterminate form. Since it was an indeterminate form, I wrote that the limit of the numerator is equal to 0 and the limit of the denominator is equal to 0. Therefore, L'Hopital's rule applies. I then applied L'Hopital's rule by taking the derivative of x minus 2, giving me 1. The derivative of 3x cubed minus 6x squared plus x minus 2 gave me this in the denominator, and then I tried direct substitution again. And that's how I got my answer here for number 2. Great. Number 3. Let's check this out. For those of you who remember chapter 1, this should look familiar in terms of our special trig derivatives. We could use our special trig derivatives in order to do this one, but we're going to use L'Hopital's rule as well. So let's do the direct substitution first. What happens if we plug in that 0? We get sine of 6 times 0 divided by 0. And so sine of 0 is 0, so I have 0 over 0, which is indeterminate form. Nice. Now, what does this work look like, especially on the AP exam? I'm going to say here that the limit as x approaches 0 of sine of 6x is equal to 0, and the limit as x approaches 0 of x is equal to 0. Therefore, L'Hopital's rule applies. And we're going to say then we're going to do our L'Hopital's rule. So what's that going to look like? Well, it's going to be, we're going to say the limit of this original expression, sine of 6x divided by x. If we take the derivative of the numerator, we would need to use the chain rule. So the derivative of the outside derivative sine is cosine. The inside stays the same, but I need to multiply by the derivative of the inside. The derivative of 6x is 6, and then the derivative of x is just 1. So I'm going to try again, plugging that direct substitution in, plugging that 0 in. That's going to give me cosine of 6 times 0 times 6, all divided by 1. Cosine of 0 from our unit circle is 1. So this is going to be 1 times 6 over 1, which is just 6. And that is going to be my answer for this problem. I know that I'm done in this because I got an actual numerical answer. Sometimes when you do these, you get like another indeterminate form, which would be an indicator to keep going in this problem. And we'll see an example of that next in problem number 4. Great, let's check it out. Number 4. The limit as x approaches 0 of 1 minus cosine of x divided by x squared. Let's try plugging in first. If we do that, we got 1 minus cosine of 0, all divided by 0 squared. Cosine of 0 is 1 again, so that's 1 minus 1 over 0, or 0 over 0. So this is indeterminate form. All right, that's my side work. Again, I'm not saying that that's equal to the original expression. We would never want to say that that is actually equal to 0 over 0. So what does this look like? Well, again, if we're showing our work, we're going to say that the limit of the numerator is 0. And I guess I'll do that over here. The limit as x approaches 0 of the denominator is 0. Therefore, L'Hopital's rule applies. And so what happens if we do that? Let's use that L'Hopital's rule. So let's do that in red. So the limit, this is going to be equal to the limit as x approaches 0 of the derivative of 1 is 0. The derivative of negative cosine is positive sine of x. And then the derivative of x squared is 2x. What happens now if I do direct substitution? Well, I then have sine of 0 over 2 times 0. Sine of 0 is 0. 2 times 0 is 0. Uh-oh. We have indeterminate form again. We have indeterminate form again. So I'm going to not say that this is equal. I'm going to sort of have this as side work again. But that means that I can apply L'Hopital's rule again, because we can apply L'Hopital's rule anytime we've got indeterminate form. And sometimes taking the derivative of the numerator and denominator again will simplify the expression and allow me to actually find that derivative. So I'm going to do the same work that I showed up here. I'm going to show that the limit as x approaches 0 of the numerator, sine of x, is equal to 0, and the limit as x approaches 0 of the denominator, 2x, is equal to 0. So L'Hopital's rule applies. And we're going to move on to the next step, which hopefully is the last one. We'll see. So green. So that expression then is going to be equal to the limit as x approaches 0 of the derivative of the numerator. So derivative of sine of x is positive cosine of x. And the derivative of 2x is going to be equal to 2. So notice here, this is actually really nice. I had an x squared. I took the derivative, I had a 2x. I took the derivative again. It's just a 2. Now there's no way when I do the direct substitution that I'm going to have an indeterminate form, since there's no way that denominator can equal 0 now. So this is hopefully leading me towards an answer. Let's see what happens when we actually do that direct substitution. So cosine of 0 divided by 2. Cosine of 0 is 1, and that's being divided by 2, so my answer here is 1/2. So this one was a little bit longer because we had to do L'Hopital's rule twice. Right? We did it once, we did it again, but it got us the answer. We were able to find the limit anyway, and that is problem number 4. Number 5, I'm going to quickly show this one. Notice here we have the limit as x approaches infinity. We talked about strategies for finding limits towards infinity. Specifically, I think it's easier to use the strategies that we talked about back in chapter 1 instead of using L'Hopital's rule, but I do want to show that you can use L'Hopital's rule in order to do this as well. So let me remind you of what we talked about for limits specifically going to infinity. We had this rule that we talked about that was called FEPL, which said that we do factorials grow fastest, then exponential functions, then polynomial functions, and then logarithms. And so they are going from fastest to slowest. And so if something's going to infinity and it's a fraction, immediately I'm seeing, okay, hey, this is a polynomial function, right? 2x squared. And then I have an exponential function in that denominator. If this is going to infinity, exponential functions grow faster than polynomial functions. So I would expect the denominator to get very large here. And so this is telling me that this is going to go towards like 1 over infinity, which is going to be 0. That is the fast way that I would do this problem. Remembering that shortcut, this like FEPL, to remember the order, right? Factorials are faster than exponentials. Exponentials are faster than polynomials. Polynomials are faster than logarithms. Great. So that's well, at least that's the old way for doing number 5. How would we do this with L'Hopital's rule? Well, if we were to do direct substitution, this is like 2 times infinity squared divided by e to the 2 times infinity. That's going to approach infinity over infinity, which is indeterminate form. Now, if this were the AP exam, I would want to break this numerator and denominator into their own limits, show they're both equal to infinity, say that L'Hopital's rule applies. You should do that, but for time purposes, I'm going to not in this one. So this limit, using L'Hopital's rule, is going to be the limit as x approaches infinity of the derivative of 2x squared, which is 4x, and then the derivative of e to the 2x by the chain rule is 2 times e to the 2x. Which, if we simplify, this is the same thing as the limit as x approaches infinity of 2x over e to the 2x. And again, what we can do is we can try doing our direct substitution here. And if we do that, we end up with 2 times infinity divided by e to the 2 times infinity, which again is approaching infinity over infinity, which again is in determinate form. So this is a case again where after doing L'Hopital's rule and trying direct substitution again, we still have indeterminate form. So we're going to apply L'Hopital's rule again, hopefully getting us to an answer here. So this expression here is going to be equal to the limit as x approaches infinity for the derivative of the numerator, which is just 4. That's a good sign, because now when I substitute in infinity, there's no way I'm going to have a 0 or infinity up there. This looks like it's going to get me towards an answer. And actually, I'm sorry, but we're looking at this one. This is our simplified one. So the derivative of 2x is 2, and then the derivative of e to the 2x by the chain rule is 2 times e to the 2x, which can simplify. So this is the limit as x approaches infinity of 1 over e to the 2x. And again, we can try plugging in, doing direct substitution. This is going to now equal 1 over e to the 2 times infinity, or 1 over infinity, which is 0. So this is one where, if we recognize at the very beginning of this problem that this is a limit towards infinity, and we remember our rules from chapter 1, this is a easy and fast problem, right? You can use that old rule and show that the limit is equal to 0. If you don't remember that and you're on the AP exam and you're like, hey, I want to use L'Hopital's rule, this is one where we just would need to apply it twice in order to find out that limit is 0, but they get us the same answer either way. All right, last bit for this topic, number 6. Reminder, as what I said earlier, L'Hopital's rule is not the quotient rule. Those are not the same thing. In this packet and throughout this, be careful. Some of these problems are asking for limits, like we see here, limits, but some of them are asking for just straight derivatives. This is not a limit problem. I would not apply L'Hopital's rule for this. This is the derivative of a fraction, of a function being divided by a function. I would have to apply the quotient rule here. So we need to be careful. We know L'Hopital's rule is only for limits, and only for limits that are an indeterminate form when you do that direct substitution. Just a reminder for you from back in chapter 2 what the quotient rule looks like. The derivative of f of x divided by g of x, the quotient rule, is low d high, so g of x times f prime of x minus high d low, f of x times g prime of x, all divided by low squared, so g of x quantity squared. So low d high minus high d low all over low squared. That is how I memorize the quotient rule. And we're going to need to apply that here because it's asking us the derivative. This is not a limit problem. So I can't just do the derivative of the numerator divided by the derivative of the denominator. That is not what would apply here. So let's just review how we'd go do that old way. This is our f of x in the numerator. This is our g of x in the denominator. So g of x is equal to x times the derivative of the numerator, so it's times 6 cosine of 6x minus f of x, which is sine of 6x, times the derivative of the denominator, which is 1, all divided by the denominator squared. So this expression here would give us the derivative function for sine of 6x divided by x. Notice that it's not the same thing. L'Hopital's rule does not apply here because this is not even a limit problem. It only works for limit problems, and it only works for limits that are in indeterminate form. Nice. That's it for new content for Chapter 4. As usual, we've got the practice. We've got solutions posted. We are hoping that you come to class with some questions. If you've got any that you would like to talk about, I'd love to discuss those in class. Good luck on your mastery check, and have a great rest of your day.